The plan for the next month or so is to talk about logs and exponentials. And the way we're going to break it down, chapter 7 is the pre-calculus part. And a lot of that is going to be a review for you guys because you've done logs and exponentials before. A lot of it's going to be very familiar. There will be some new stuff. But then chapter 8, that's the calculus part, and that's where we talk about limits and derivatives using logs and exponentials. But we're going to start with the pre-calc part. And what we're going to do for the first part, we're going to talk about exponentials first and then logs. And one of the first things we're going to focus on is the graphs. Because if you can understand the graphs of a log and exponential, then it helps you understand what you're doing with each function. So first of all, this is what I mean when I talk about an exponential function. I basically mean the variable is the exponent. So in its simplest form, it would be y equals b to the x for any number b. So it could be y equals 2 to the x, y equals 10 to the x, or actually I should say any positive number b. So yeah, b is the base, that's the name for it, that's our vocab word, and it does have to be a positive number. We're not going to do negatives for exponentials, that's a different type of function. And as I mentioned a minute ago, we're going to focus on graphs. And what we're going to do is we're going to add it to our library, and then we're going to do transformations again. So let's talk about some basics about exponentials. An exponential graph always starts very close to zero. Starts very, very, very small. And it grows, but exponential growth means it's growing very slowly at first, and then a little faster and faster and faster, and it keeps growing faster and faster and faster. And at the end, it's growing very fast. So basically, let's kind of start piecing a sketch of a generic exponential function. Now, because it starts very close to zero, every exponential graph starts with a horizontal asymptote at zero, or the x-axis. And way, way, way off to the left, it starts very small, very close to zero. It's basically almost touching that asymptote. And then it kind of slowly curves up until eventually it's going almost straight up. So an exponential looks like this. It starts here by the asymptote, and it's growing slowly, 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 and then faster and faster and faster. And then at the end, you have that arrow that's almost pointing straight up in the air. Now, as far as our graphs, I'm going to have you guys focus on 2 points on this graph. Now, the first one is going to be the point 0, 1. And the second one is going to be 1, and then b, whatever the base is. And that's the difference between each one. That's how 2 to the x is different from 10 to the x. So first of all, let me show you real quickly where I got these numbers. If my function is y equals b to the x, and I do a quick xy table, and I just plug in the numbers 0 and 1. Let's say I say 0 and 1 are the easiest. Let's just plug them in and see what we get. Well, if I plug in 0 for x, I get b to the 0 power. Now our rule for exponents, anything to the 0 power equals 1. And that's why 0, 1 is on every exponential graph. It doesn't matter what the base is. It doesn't matter if it's 2 to the x or 1 million to the x, because anything to the 0 power is 1. Now for my second value, if I plug in 1 for x, I get b to the first power, which is just b. And that's where those 2 points come from. I mean, it's a very simple concept saying the 2 easiest x values to plug in are 0 and 1. If I plug in 0, I'm going to get 1 no matter what the base is. And if I plug in 1, I'm going to get the base, whatever it is. So keeping that in mind, for our first example today, let's sketch 2 to the x, 3 to the x, and 5 to the x on top of each other so we can see the difference between those 3 graphs. And what I'm going to do, I'll do this first part in red. The 2 things that we just said are going to be the same on every one of those graphs are that you have this asymptote here at 0, and you have a point right here at 0, 1. So those 2 things are the same for all 3 graphs. The only difference is where that second point lines up 1, whatever. So let's say I'm going to graph, say I'm going to graph 2 to the x first. I have my asymptote, I have my first point, 0, 1. Because the base is 2, the second point is 1, 2. So I go over 1 and up 2, and I put a point right there. Now those 2 points are all you need because we already know the shape of the graph is going to look like this. All you have to do is draw that curve starting at the asymptote, going through both of those points, and then curving up like that. So that would be an example of 2 to the x. Now let's do 3 to the x. So again, I'm going to use the 2 red parts, the horizontal asymptote and that first point I drew right here. Those are parts of all 3 graphs. Now if I'm drawing 3 to the x, the only difference is that second point is going to be 1, 3. So I go over 1 and up 3, and I put a point right here. And what you get is a graph that looks almost the same, but it turns up a little bit more sharply. It's a steeper curve. So it looks the exact same at the beginning over here. Goes through the red point and then the purple point, and you can see it just turns up a little bit faster. Let's go ahead and do 5 to the x. So 5 to the x, again, on the left-hand side, it's going to look almost the same as the first 2. The difference is on the right, it's got to go through the point 1, 5, which is up here. So it's going to turn even more sharply like that. So you can see if you look on the left-hand side of our graph, you have 3 that you can barely see the difference. They're kind of all on top of each other. There's tiny, tiny, tiny differences in those graphs, but where the big difference comes in is on the right. The blue one, 2 to the x, has kind of a smoother curve. Purple turns a little bit more sharply, that's 3 to the x. Green turns very sharply. And if I did like 10 to the x or 100 to the x, it would turn almost straight up in the air. So basically the idea is every exponential graph looks like this. You just use that second point, 1, b, to give you an idea of how sharply it's turning. All right. So now let's focus on transformations. We've done transformations a couple times this year. And basically what we're going to do is we're going to say, so here is my function we just talked about, b to the x. What if there's other numbers in there? You know, what if it's 2b to the x, or b to the x plus 5, or something like that? And we're going to do the exact same transformations that we did back in chapter 1. Basically, like you have this a right here, that's multiplying, that's going to do something. This k right here, that's a number that's being added to my function. Same thing. That's going to do its own transformation. This h, if I add or subtract something to the exponent, what does that do? So a, k, and h, it's the same a, k, and h we talked about in chapter 1. I'm going to go through it real quickly with you guys. There is a video on it back from chapter 1. If you want to get a little bit more in detail, you can look at that. But basically, in order, kind of from left to right, the k is a shift up or down. It's just going to take that graph and it's going to move it, slide it up or down, depending on whether it's positive or negative. The h is a shift left or right, and I put in parentheses it's backwards. So remember, if it's the opposite of what you'd think. If it's x plus some number, it actually shifts to the left, and if it's x minus some number, it shifts to the right. A is going to be a stretch, and that's really the hardest transformation to do. It's the only one, we called it non-rigid back in chapter 1 because it changes the shape of the graph. It can also be an x-axis reflection if it's a negative number, meaning it'll take that graph and flip it from the top down to the bottom. So instead of above the asymptote, it'll be a mirror image below. And if the x is the variable itself, the x is negative, that flips it left and right, and I'll talk a little bit more about that at the end of notes. So basically, these are our transformations. If you need to go back and watch the video again, you can. It's from chapter 1, but we're going to go over some examples, and I think that'll remind you of it anyways. All right, so let's do this one first. We're going to graph f of x equals negative 3x plus 1 plus 3. And the first thing I want to mention here, let me recopy the question real quick. We already said, that was on our very first slide today, I said the base has to be a positive number. So the base here is not -3. The base is 3. In fact, the reason I'm recopying it is when you see a question like this, I want you to, whether you recopy it or not, I want you to think of it as -1 times 3 to the x plus 1 plus 3. So the -1 is actually going to be a reflection. The other thing is I put the +3 on the end. In the notes, the k was on the beginning. It doesn't matter if it comes before or after. If you're adding a number to your function, that's k. So basically, let's kind of make a list of our steps here. So step 1 is going to be just start with y equals 3 to the x. I can see that that's my base exponential function. The base is 3 in this problem. So before you even worry about transformations, let's just start with 3 to the x. Then let's do each transformation. So I look at this -1 here, and I say, oh, this is a reflection. And you could say it's a reflection, you word it however you want. It's a vertical reflection, a reflection from the top to the bottom, or a reflection over the x-axis. There's a lot of ways to say it, but just understand it's vertical. It's going to flip from the top to the bottom. So I'll put reflection, I'll put up, down. We don't have a stretch here because it's a -1. If it was like a -2 or a -10 or something, we would also have a stretch. So the only other transformations are stretches. And I'm going to do this one right here. I'm sorry, not a stretch. We don't have a stretch. We have a shift. So we're going to shift this. That would be up 3. Remember, the k is very straightforward. Positive means shift up, negative means down. This is the one that's backwards. So it's a +1, and whenever you're working with a graph and you think plus, you always think to the right, positive to the right, negative to the left. This is actually backwards. So we're going to shift it left 1. Oops, left. Okay, so I'm going to go ahead and draw each step right now, and I'm going to go in the colors that match my how I wrote it over here. So let's start with y equals 3 to the x, which means it'll have an asymptote here at 0. It'll definitely go through the point 0, 1, they all do. And because my base is 3, I go over 1 and up 3, and I put a point right there. So my first graph looks like this. It's actually the exact same one the middle one we just did on our last example. Okay, now for the next step, we're going to reflect from the top to the bottom. And basically, what you want to do with these reflections is don't think of it as the whole graph, just focus on those 2 points. Like that point 0, 1, instead of up 1, make it down 1. And that point 1, 3, instead of up 3, make it down 3. Now come from the bottom of the asymptote and go through those 2 points, and what you have is a perfect reflection. So we're going to really focus on the asymptote and the 2 points to do all of our transformations. Okay, now all we have left is the shifts, and I usually do those 2 at the same time. I don't need to do like each one as a separate step, but one thing I do want to mention here before we move on is this shift up is the only one that will also move the asymptote. A stretch, a reflection, a shift left and right, none of those move a horizontal asymptote, but a shift up 3 will. So when I go to draw my final answer, I'm going to do that first. I'm going to count up 3, and I'm going to put my asymptote right here. Because when you shift the graph up or down, the asymptote shifts with it. Now, to finish the graph, we're working from the purple one, always the most recent one. Go focus on the 2 points again and take each point and go up 3 and left 1. So if I take that point in the middle and I go up 3 and left 1, I would have a point right here. And if I take this point and go up 3 and left 1, I would be actually right on the origin at 0, 0. So for your final answer, and it looks kind of messy because I have 3 graphs on top of each other, come from your new asymptote, turn down through those 2 green points, and that'll be your final answer. So the green one is the final answer. I drew the blue one and the purple one just to show work, but really the green one is the final answer. It's a 3 to the x graph that's been reflected and then shifted up 3 and left 1. And my colors, my 3 different graphs show the steps. Blue is just 3 to the x, purple is 3 to the x with a reflection, and green is 3 to the x with the reflection and both shifts. And this is exactly what we did back in chapter 1. It's just a new graph that we're doing it to. All right, we'll do another example in a second, but before we do that, I want to talk about the number e. Because really the most common exponential, the one that you're going to see more than anything else, is e to the x. You know, when I talk about the natural base e, I'm talking about e to the x. So let's talk about what that number is, you know, what it means and what it comes from. So here's the actual mathematical definition of the number e. It's a limit question, and it's the limit as x approaches infinity of 1 plus 1 over x to the x power. Now, basically what it is it's an irrational number. It's very much like pi. So I always tell students, I'm like, when you're doing geometry, pi is like the number, you know, and it's about 3.14. But it's a very important number and it just naturally occurs. Same thing with e, it's just algebra instead of geometry. The number itself comes out to about 2.7. And if you're doing an e to the x graph, a lot of times people think, oh, that's so much harder. You know, I can do 2 to the x, I can do 5 to the x, but e to the x, no, that's hard. It's not. It's just basically like 2.7 to the x. So I said just approximate e for now, for graphing, just approximate it to be about 2.7, and then graph it like any other exponential. So let's do one of those. Here's our graph. G of x equals 2 times e to the x minus 2 minus 3. And let's go through the same steps we just did. You know, first of all, I just look at the exponential itself, and I say I'm going to start this graph with y equals e to the x. And then I start walking through my transformations. Multiplying by 2 is going to be a stretch. So I'm going to stretch this thing by a factor of 2. There are no reflections because the 2 is positive and the x is positive. Those are the 2 things I would be looking for a reflection. So just like last time, we'll finish it off with a shift. And we will shift down 3 and right 2. So see how I just walked through the equation and I just looked at each number one at a time and asked, what does it do? What does that first 2 do? What does that negative 3 do? What does that minus 2 do? And then once you make your list, it's just going step by step. So let's start with e to the x. So I said it's an exponential. So remember, every exponential has the same 2 things. Has an asymptote at 0 and a point at 0, 1. Now, the second point for e to the x, remember, is about, the squiggly equal sign means about, 2.7. So for my second key point, what I'm going to do is I'm going to go over 1 and up about 2.7, just to go up not quite all the way to 3. And in fact, the graph of e to the x and 3 to the x looks so similar that if you weren't marking points, you wouldn't be able to tell the difference between them, because it's just a tiny, tiny difference. Okay, so e to the x looks like this. Looks almost exactly like 3 to the x. All right, step 2, we're going to do our stretch. Now, when you're stretching times 2, I said just focus on the 2 points. Take the height or the y value of each point and multiply it by 2. So like right here, that first point, instead of 0, 1, is going to be 0, 2. That one moves up 1, basically. And the second point, remember the second point, the height was 2.7. If I double that, it would be about 5.4. 2.7 times 2 is about 5.4. So I'm going to count up 5 and about 0.4, just approximating, and I'm putting a point right there. So that's how the stretch can be easy if you just focus on points. Just take your two key points that we're working on and take the height of each one and double it. Now start from the asymptote and curve through those 2 points. And you can see this graph, now all of a sudden it doesn't go through that 0.01 anymore. The transformations can change that. So now it goes through 0.2 instead of 0.1. Okay, to finish this graph, we're going to shift down 3 and right 2. And remember, the shift up or down will take the asymptote with it. So as soon as you realize you're shifting down 3, the first thing I'm going to do is I'm going to go draw in my new asymptote at -3. And when I'm ready to draw my final graph, it's going to go from there instead of the blue one. But before I can draw the final graph, let's do our 2 points. So from the green one, each point needs to go down 3 and right 2. So if I start in the middle, 1, 2, 3, 1, 2 would be right here. And if I start from the top green one, it would be, now we kind of track it. Remember, we were at about 5.4. You can call it 5.5. It's not that big a deal. Count down 1, 2, 3, and then over 2 would be there. Now from the new asymptote, draw your curve that goes through those 2 points, and the purple one is your final answer. So that's 2 different examples of transformations. One of them was an e to the x, and my main focus for that is just for you guys to realize it's not any harder. E to the x is not any harder to graph than 3 to the x. And then focus on each transformation. So this is our last one for today. We're going to graph f of x equals 1/2 to the x and 2 to the -x. And then we're going to realize something about these 2 graphs. So first of all, f of x equals 1/2 x. It's for the first time we've seen a base that's less than 1. So let's graph it. Now it's still exponential, so it still has those same 2 things. It has an asymptote at 0 and a point here at 1. But here's the trick. For the second point, it's over 1 and up 1/2. It's lower than the first point. Now what that means is it's been reflected, basically. It means the graph is approaching the asymptote to the right and rising to the left. So the only way that you can have an exponential graph with those 2 points in that asymptote is if it's going towards the asymptote this way. That wasn't a very good one. And then turning up this way. And that would be f of x right there. So that's one thing you want to know. If your base is less than 1, it flips the graph. It's up to the left and down to the right instead of vice versa, or towards the asymptote to the right. Now, when I go to graph g of x, let's use our transformations. Let's say I'm going to start with y equals 2 to the x, but then this negative right here, that's the one that reflects left and right. It's the one that flips it this way. So if I start with 2 to the x, let's use the red again. I have my asymptote and I have my point at 0, 1. My other point would be 0, 2 right here, and I would have this graph right here. Now, the key is, these are the exact same graphs. If you reflect the green one, it turns into the blue one. So that's the point I wanted you guys to realize here. F of x and g of x are the same graph. And the reason is, really, if you look at the 2 equations, 1/2 to the x and 2 to the -x, 2 to the= equals 1/2. So 1/2 to the x and 2 to the negative 1 to the x are the exact same thing. So just one last little interesting note. Number 1, g of x, that's the first time from our examples today that we did the horizontal reflection. I wanted you guys to see that. And number 2, I wanted you to realize you don't even really need that one because you can always change your base to a fraction and get the same result. All right, so that was actually kind of a long video on exponentials, but hopefully it was a good review for everyone. And we want to make sure we have these graphs down before we move into logs.